In this video I'm going to give you a brief introduction to potassium channels. The first thing to realise is that there are actually four main kinds of potassium channel. We have probably the best one you would have heard already is the voltage gated. But we also have inwardly rectifying. I'll explain what these are in a moment. Tidy that up a bit. Calcium activated. Calcium and we have the final one are called the tandem pore domain. I'll explain all these in just a moment. So all of these are tetramers, that is to say that they're formed of four subunits so that's not very well drawn. Let me just redraw that because they do actually join together. They're formed of four subunits which line the central pore, and of course it's the pore is where the potassium channels go. Okay, so let's have a look at these in turn. So let's start with the voltage gated ones, which if we have the membrane like this, each subunit voltage gated channel has an intracellular N-terminal domain, and then it has 1, 2, 3, 4, 5 transmembrane regions like this, and then they have a pore forming domain which kind of does that, and then there's one last transmembrane subunit region like that. So 1, 2, 3, 4, 5, and that's the 6th transmembrane domain, and this is the pore forming loop just here. So they're voltage gated, which means that if you record their conductance against voltage, typically what you find is that they don't conduct at negative potentials, but then as you get more and more positive potentials they start to open. So these are typically the ones that help with the repolarization of the action potential here. So that's the voltage gated ones. The other ones we need to look at now are the inwardly rectifying ones, and these are going to be represented in blue. These have a slightly different structure in that they have this time just two domains separated by a pore forming loop like this. So 1 and 2. Alright, so these, the reason why we call them inwardly rectifying is if we do the same voltage plot here, what we find is that they prefer to allow potassium into the cell but don't let it out quite so much. So what you find is that they have the same tend to have slightly leftward shifted voltage activation curves. This is conductance and this is voltage. But remember that if EK is somewhere around here, what happens is although the reason they have this ability to stop potassium leaving the cell is because they have a slightly unusual property that when they're depolarized, they close. So they're usually open at hyperpolarized potentials, but they close when they're depolarized. So what typically happens when you steadily depolarize them is you get, at hyperpolarized potentials, you get this inward potassium current. There may be a slight outward, but then it closes like that. So it tends to prefer potassium entering the cell. And the reason they're able to do this rectification is because they have quite an unusual property, which is that depolarization actually closes the channel. And so what happens is at very negative membrane potentials they allow, so this is now current and this is voltage, they allow potassium in, but when the potentials sort of get a bit positive they close. So that means potassium can go this way but not that way. So another group then we have are the calcium activated channel. So let's have green for the calcium activated channels. These are the same structure as voltage gated ones. So for 5 transmembranes here, I lost count there. So 5 transmembrane domains, then a pore, and then the 6th one, just like that. And these are actually activated by calcium. So typically they'll be closed, and then when intracellular calcium binds the intracellular face, the channel opens, and then potassium can usually leave the cell. Now these tandem pore domain ones are, because they're so interesting, they're going to be a multicoloured one, and they have, maybe I shouldn't have chosen multicolour, I don't know, they have start off with 2 transmembrane domains, begin to regret the colour scheme now. Oops, I've made a mistake here. I don't quite do this. Let me just get rid of that pore. Let me just fix that. Right, so they have a loop like that. So far, they look a bit like inward rectifiers, but watch what happens now. They actually have another one, just like that. So they're a bit like two inwardly rectifying ones stuck together, and they more or less stay open all the time. So they act a bit like constant leak channels. So these are your leak channels, and these are involved in the resting membrane potential. These are involved in responses to drugs, responses to ligands, I should say, neurotransmitter, and these are also involved in setting the resting membrane potential. So there we have the 4 types of potassium channel, and that concludes our introduction to these ion channels.